Did you know that we know what the center of our galaxy smells like?
How do you know these things?
This is a tough place for sensitive people, but we need them badly.
Please try to enjoy each fact equally and not show preference for any over the others.
As we were talking about, the lowest note on the piano is an A0, which is a 27.5 hertz. So what's the lowest note ever? The lowest note ever recorded was the Perseus black hole. Perseus
pull us down close to the horizon,
which is 57 octaves below middle C. And again, middle C is here. This is C4. I think about that for a second. This is C4, middle C. So this is C3, this is C2, this is C1, and C0 is, again, below what the piano can actually play. So we're going 57 octaves down from here. That is extremely subsonic. Cannot hear that. How do they measure that? That's for another video. What's the lowest note that a human being has ever sung? Well, that honor belongs to someone named Tim Storms.
Do, ti, la, so, fa, mi, re, do.
Wow.
Wow. Who sang a G-7. So again, this is a G1. Pretty low. That is, bass guitar range. That's G1. Tim Storms sang a G-7, which was 0.189 hertz. So again, very subsonic. Only specialized equipment can actually detect that. So what if we go the other way now? We talked about going above 20,000 hertz where humans can't hear. We talked about how 60 years old exactly is 21,915 hertz. What's the highest note that a human has ever sung? Well, that distinction belongs to someone named Georgia Brown, who sang a G10.
Boy, you're gonna wake us, baby. I only wanna wish you for someday. Essa você conhece?
Acho que é assim que fica perceptível, né? Não é?
E tem outros também. But I wanna way for you. Desde pequeno.
É tão apurado que fica quase que inaudível no final.
Chega a ficar... porque quanto mais fica agudo, né, mais vai sumir na nota, assim, ó. Aí vai ficando...
Which is actually just above that 60-year-old E10, 21,000 hertz. That is 24,600 hertz. She's saying that. Again, humans would not be able to hear that. Specialized equipment would need to be used to register that. So let's go a couple more steps. Let's get really, really up there with this. Again, we're well beyond the point. This is hypersonic, supersonic. Humans can't hear it. Bat echolocation is 200,000 hertz. Now, I did not actually look up what note this corresponds to, but obviously we're 10 times above, the E10, the 60 years old, so we're way out there. Thermal vibrations, aka atomic sound, the vibration of atoms, is 1 trillion hertz. 1 trillion hertz. That's how fast atoms vibrate. And we're made of those. How does that work? And the highest one, according to my research, the ceiling of how fast things can possibly vibrate, the laws of physics, the Planck limit is 10 to the 43 hertz. I don't even know what number that is, but that's what it is. But wait, there's more. Not only do I have those fun facts, but I'm going to get even more nerdy here because, hey, I'm the sensory nerd, right? So I was watching a video the other day about oddly enough, the deepest hole ever drilled in the Earth, the Kola Super Deep borehole, if you're not familiar. And in that video, it mentioned some other distances because the hole was drilled a certain distance, and that got me thinking, if we can take ages and we can convert those into hertz and convert that into notes, we could do the same thing with depths or heights. So I'll put these up on the screen for you, but in terms of the Earth's internal layers, the mantle and the core, there is the crust, the upper mantle, the lower mantle, the outer core, and the inner core. And so the crust would be 0 to 35, so that's C sharp 1, 35 kilometers would be 35 hertz. The upper mantle goes to 670 kilometers, or E5. The lower mantle goes to 2,891 kilometers, or hertz, that's F sharp 7. The outer core, 5,150 hertz, kilometers, E8. And the inner core goes starts at 5150 and goes to 6,371 kilometers, or hertz, which is G8. The ocean depth zones, which are called the pelagic zones, those are the epipelagic zone from 0 to 200 meters. So 200 hertz is G3. Mesopelagic is from 200 to 1,000 meters. 1,000 hertz is B5. Bathypelagic zone is up to 4,000 meters deep, and that is a B7. Abyssopelagic is down to 6,000 meters, and that is an F sharp 8. And then hadopelagic, I don't actually know how to pronounce that one. Hadopelagic, I'm going to say, 11,000 meters, that is an F9, which is actually pretty close to what we were talking about with one of the ages, right? And then lastly, thanks for bearing with me here, the atmospheric layers, in case you didn't know. So the troposphere, which goes from 0 to 12 kilometers, 12 hertz, is actually G minus 1. The stratosphere goes up to 50 kilometers, 50 hertz is G positive 1. Mesosphere goes up to 85 kilometers, and that is an F2 in hertz. The thermosphere goes up to 600 kilometers, and that is a D sharp 5. And the exosphere, which goes up to 10,000 kilometers above the surface of the Earth, 10,000 kilometers, 10,000 hertz, is a D sharp 9, which again we talked about with age 10 or 11. I forget which one it was now. And that's where satellites orbit, and it's the edge of space. So the edge of space is a D sharp 9. Who knew? Now you do. Nerd! One more fun fact for you. I'm trying to make this video really worth your watch time, okay? So my chart here, which you will find on my Patreon, and I will, I'll make it available. This is the chart that I made that does the math for you. So it tells you every frequency in hertz and what note it corresponds to. But something that I didn't know before I got into all of this learning was that each note, and I'll put an overlay on the screen for you over here, right here, each note, so every note, the next octave up is exactly 2 times the number, 2 times the frequency. So the very simplest examples, you've got, okay, that doesn't quite work. So a C sharp minus 4 is 1.1 hertz, and then C sharp minus 3 is 2.2, then 4.3, and it goes up from there. With E, so this one I noticed. So E2 is 5 hertz, approximately 5 hertz. E1, sorry, E minus 2. E minus 1 is 10 hertz. E0 is 20 hertz. E1 is 41, so we're starting to get up, and then 82 for E2. So it's doubling every octave. And this is why when you look at spectrograms, which you will see in another video, you'll see that there are lines that go up. It's like a ladder. It's a harmonic ladder. And that's because of this. So when you're hearing what sounds like just one note, you're actually also hearing a harmonic reverberations.
I didn't know that.
Cool, huh? And that reminded me from the noise cancellation video, this little guy, our little friend, the +2. So every octave of the same note is, it's not +2, it's ×2, but there's no ×2 Uno card. So I'm doing my best here with what I got. So as I said, every semitone, so every key from one key to the next on a piano, that each one is a semitone. Every single one of these is exactly, the pitch, the frequency of that pitch is exactly 5.9463% more or less than the one next to it. So that is how we have 365 hertz in 44-ish keys, and then we have 10 times that in the next 44 keys, because a 0 is 27.5 hertz and a sharp 0 is 29 hertz. So that's a 2 hertz difference approximately. But way up here, we're talking about more like 900 hertz difference, because every single semitone climbing up is 5.9% more. It's compounding, like compound interest in a bank. And if you feel comfortable doing so, please feel free to leave a comment and drop the note of your age. And other people will see if we can guess it. Or not so much guess at the charts there, but you know what I mean. I'm Lacey, the Sensory Nerd. Thanks for watching and learning with me.